Hello, Dr. Oh and Dr. Hilmi. So for integrated design project for cost process plant design and material science for chemical engineering, we are from Group 1 and our title for this project is production of phenol from cumene. In this case study for cost process plant design, our group topic is regarding phenol production where the process flow, simulation, selected material, calculation and unit chosen are further discussed in this report in terms of what we have learned throughout the entire course and apply that particular knowledge in this phenol production case study. The main objective of our report is to design the production plant for phenol in industry. Phenol is an aromatic compound with an OH group bonded to the phenyl ring and it is used in the production of disinfectants, dyes, pharmaceuticals, plastic and many more. Nowadays, consumption of phenol largely follows the patterns of the leading world economies. Besides, the other objectives are to enhance phenol production in industrial scale by applying knowledge gained in process plant design course in terms of chemical reaction, simulation, material balance and design parameter. Next is to calculate various aspects of the chosen unit in phenol production process such as material selection, thermodynamic properties, corrosion resistance and safety precaution in order to achieve high efficiency of phenol production from cumene.
Hello, Dr. O, and fellow viewers. My group, Group 1, was given the process where cumene is converted to phenol. By the way, my name is Mayappan Mahesh. So we were given a simple flowchart. And from that flowchart and doing a lot of immense research, our group, we managed to finalize on this process flow diagram. Now there were a total of 2 process flow diagrams that I created. The first one is obviously this one shown here. The second one is the one after carrying out the heat exchanger network design calculations. In the symmetry simulations, the separator, which is after the splitter, and the washing tower are not included. In simple, raw cumene, air, and sodium carbonate, which is used as buffer, enters the oxidizing unit, where oxidation obviously takes place. And cumene hydroperoxide is formed. Now the cumene hydroperoxide enters the splitter, where it is deformed by using acid. And then from there, the deformed cumene hydroperoxide enters a separator to separate the acids. The acid now, the sulfuric acid, is recycled back to the splitter. The stream is sent now to the washing tower. Now the washing tower's main purpose is to wash off the remaining acids present. After washing off, now the stream is sent to our first distillation column, where the top product or the light key acetone is removed and then is stored in a tank because acetone is expensive. It can be sold. The bottom product now enters our second distillation column. Now here the top products are the recycles and the bottom product is sent to the third distillation column. At the third distillation column is where we separate phenol from our bottom product and the phenol is stored in the storage tanks before it is sold. Now for the recycled stream, it contains mostly cumene and acetone and is recycled with hydrogen before being sent to the oxidizing unit. Now shown here is the symmetry simulation done. The process flow diagram was very important to get the overall flow for the symmetry simulation. But from the symmetry simulation, we managed to get the stream details, which were then used to complete our process flow diagram, the table down there. Now for symmetry simulation, we did not include 2 things. Firstly, the separator after the splitter, and secondly, the washing tower. And replacing the splitter, we used the cleavage unit, and replacing the first distillation column, we used a flash distillation unit.
Next, I will talk about the heat integration for this project. First of all, we extract 2 hot stream and 2 cold stream from the process flow simulation, and we find out the source temperature and the targeted temperature for each stream. Next, the heat capacity flow rate can be calculated by using the specific heat capacity, multiply with mass flow rate and divided by 3600 to convert it into kilowatt per degree Celsius. Next, the heat load can be calculated by multiplying Cp with the temperature difference between the targeted temperature and the source temperature. For heat transfer to occur, there must be a temperature difference between the hot and cold stream. For this project, a minimum temperature difference of 20 degrees Celsius is selected for the pinch analysis. Next, to calculate the interval temperature for the hot stream, we must use the source temperature of hot stream minus with 10 degrees Celsius. For cold stream, it must be added with 10 degrees Celsius. So this is our result. The next step of the problem table is to do the stream population. By doing so, we can find the minimum hot utility and the cold utility. Other than that, we can also find out the pinch temperature for the hot stream and the cold stream. At the utility of 0 kW, we can find out that the interval temperature is 35 degrees Celsius. Therefore, the pinch temperature for hot stream is 45 degrees Celsius and for the cold stream is 25 degrees Celsius. Then we can find out that the minimum hot utility requirement is 1202.5 kW and for the minimum cold utility requirement is 131.4 kW. Next, we can proceed with the heat exchanger network design. For our design above pinch, we have to make sure that the heat capacity for the cold stream is always greater or equal to the hot stream, while the remaining requirement will be fulfilled by using a heater. For design below pinch, we have to make sure that the heat capacity for the cold stream must be smaller or equal to the hot stream, while the remaining requirement will be fulfilled by using a cooler. Therefore, this is our result for the heat exchanger network. Stream 7 and Stream C is matched above pinch to exchange 39 kW, and Stream 11 and Stream A is matched together above pinch to exchange 643.3 kW. While Stream C and Stream A requires an extra heater to reach the targeted temperature. For the design below pinch, since Stream C and Stream A has a T source which is same as the pinch temperature, therefore no heat exchanger is required. However, for Stream 7 and Stream 11, an extra cooler is required to make sure that the temperature is cooled down to the targeted temperature. Last but not least, we can see the total hot utility fulfill the calculation earlier, which is 1202.5 kW, and for the cold utility as 131.4 kW.
Now, shown here is the process flow diagram after the heat exchanger, the second process flow diagram. The only additions here are the 2 heat exchangers and the 2 heaters and 2 coolers added after doing the heat exchanger network design. Thank you.
Assalamualaikum and hi. So moving on to the next part of the presentation. So basically our group have chosen the distillation unit column D101 as our selected unit, and as you can see from the diagram, the top product which is considered as stream 10 consists of most of the acetone, and the bottom product stream 11 consists most of the phenol, which is our main product. The selected material to construct this distillation unit column is after having a discussion and analysis, we have selected stainless steel type 31L to construct the distillation unit, as it has a lot of benefits in terms of chemical properties, mechanical, thermal and electrical properties. Thank you very much.
Okay, my name is Muhammad Madani, and today I will explain to you about the corrosion and the degradation of material of the selected separation unit, that is the distillation column. Corrosion is an electrochemical reaction where the metal is being exposed to the environment and loses its electrons. Okay, these are several components that I have been fed to the distillation column, and the properties of the reacting chemical. That is, first is the phenol. That is, the characteristic is corrosive, same as the water. But for the cumene, acetone, and acetophenone, the characteristic is non-corrosive. Okay, this is the galvanic series. That is the relative reactiveness of the metal in the galvanic series. In the increasing active in the anodic part, it will cause the lower of the corrosive resistance. So that means the aluminum alloy has much lower corrosive resistance than the other metal, that is the stainless steel and the carbon steel metal. Okay, this is the calculation formula for the CPR. That is, we are assuming the distillation column as the area of the cylindrical vessel, which is then we found the time exposure that is for the stainless steel that is the highest around 0.0725, which means that the stainless steel has much higher uh, corrosion resistance than the other material that is the carbon steel and the aluminum. Okay, next is the recommendation to improve safety aspect of the selected unit, that is the distillation column. First is the installation of the safety instrument system, that is to prevent any accident on and off of the factory, including the explosion and the fire. Second is the installation of the pressure relief valve, that is to prevent any damage to the equipment when there has the high pressure in the distillation column. That's all from me. Thank you.
As for conclusion, this integrated design project integrated the cost of process factory design and material science for chemical engineering on the design topics of phenol production plants in the industry. This conclusion is supported by the analysis performed in this report. After perform the simulation of the symmetry, the produced phenols account for mass flow of 7,189.5 kg per hour, which equivalent to the 62,980.02 ton per year. Heat exchanger network also has been done by matches between streams adjacent to a pinch meet the heat capacity limitations obtained by the problem table method. For material science part, the stainless steel which it has the highest exposure time that shows it has the high resistance than other metals.